Hello and welcome to the 11th week TS session of uh, Statistical Mechanics course. Uh, yeah, so the last couple of weeks we discussed problems on Fermi statistics. Uh, this week we'll be looking at some problems and examples on Bose gas uh, and the thermodynamics of uh, particles obeying Bose-Einstein statistics. Yeah, so let's get started. Yeah, so uh, like we did for fermions, let's start by quickly looking at this class of functions called the Bose-Einstein functions or Bose-Einstein integrals, which appear often in the calculations of various quantities. So the integral of interest is this. So Z in so so when we apply this formula, I mean, so uh, when we see this function in the calculations, the Z will be as usual the fugacity. It's e to the beta mu. Uh, for bosons, mu has to be less than the lowest single particle energy state. For a non-interacting system of bosons, the chemical potential must be less than the minimum or the least of all the single particle energy states. So yeah, so we'll be working with our setting the single particle energy state with the lowest energy with the lowest energy to zero. So mu is going to be less than zero, and we'll be interested in the case when z is less than or equal to 1. Uh, so so to get a infinite sum or a series representation for this integral, we can again expand this denominator uh, for z less than 1. And what we'll see is that it's very similar to what we did for fermions. Uh, so we will see that this uh, integral will become this series. So the n of uh, this parameter n appears here in the summation. So let's look at a few cases. So when z equal to 1, so this function for any n, uh, uh, the value of this function at z equal to 1 is so that is 1 plus 1 by 2 to the n plus 1 by 3 to the n and so on. So this is nothing but the Riemann zeta function of n. Uh, so we will be uh, uh, Yeah, we will be seeing this quantity more uh, um, in the discussion of the photon gas. So yeah, so let's just mention that this function when n is equal to 2. So this is uh, uh, the popular sum, popular series, and this is equal to pi square by 6. And when n is equal to 4, is equal to this. Okay. So we can also look at uh, let's say a case when z equal to 1. Sorry, just a minute. Yeah. Uh, so when z equal to 1, I mean, sorry, when n is equal to 1, this will be equal to, so it is z plus z squared by 2 plus z cubed by 3 and so on. So from this series expansion, we can see that this is nothing but minus log 1 minus z. Yeah, uh, we could also just do this integral when n is equal to 1 and see that this is equal to minus log 1 minus z. Yeah, so these are some special cases. What will also be useful is the derivative of this function with respect to z. So let's see what the derivative is. So remember for the Fermi-Dirac functions, we had a recurrence relation uh, which relates the derivative of uh, the integral labeled by n to the integral labeled by n minus 1. Yeah, so we expect something similar here. So let's see. Um, so this is z to the m by, so taking a derivative with respect to z. Yeah, so this is nothing but yeah, so we have written this z here outside in the denominator. So this is going to be simply g n minus 1 of z. Yeah, so the result is that it's equal to this. Okay, all right. Yeah, I think that's all maybe we need. Maybe if required, we'll try to derive uh, whenever it is required. So yeah, so let's get started with some problems. So in the uh, In the problem sets, I've seen that there are questions on black body radiation uh, in 11th week's uh, problem sets. So I have included some problems on those here. Uh, yeah, okay. So yeah, we're going to start with a problem on black body radiation, or basically the statistical mechanics of gas of photons. All right. Um, you would have seen calculation of various quantities uh, that are associated with the photon gas, the energy, uh, pressure, number of particles. I mean, the number of photons on average, and so on. So yeah, so let's start from the beginning and try to evaluate. Try to calculate these quantities that we need here. So we need the energy, mean energy, and also the entropy per photon. So we would need the expectation value of energy, expectation value of n, and the entropy. Yeah. So let's start with I mean start from the beginning. Uh, so uh, so photons are bosons, and the number of photons is not conserved. So that means that we can we have to allow various particle numbers even in the microcanonical ensemble. We have to allow states with different number of total particles. So those all would be allowed microstates of the system in the canonical ensemble. So or that is equivalent to saying that uh, the chemical potential is zero. Uh, so we have so for a given single particle state, or for a yeah. So if you have a state labeled by k bar and uh, and a polarization, it's called p. So p can take two values. So the EM radiation is or the EM waves are transverse waves. So you have two polarizations associated with a given direction of propagation of the wave. Or you can also say that uh, there are two internal degrees of freedom associated with photon, the two polarizations. And let me just write this. This is- So if we look at the uh, the partition function for a given state, for a single particle state, uh, so we know it is going to be so this is the contribution from state with one photon. Uh, this is for two photons and so on. So we know that the energy of a photon is, let me write this as k bar. This is h bar ck. So this is simple geometric series. So the partition function would be this, and uh, so we want to calculate the full the partition function of the full system. So since these are independent single particle states, the partition function will just be a product over these partition functions. And like we have seen before, uh, it's going to be equal to this, which is yeah. So now this is the partition function, or rather the logarithm of the partition function, written in terms of or rather written as a sum over single particle states. So now we can write this as an integral by introducing the density of states of these single particle states. So let's look at the density of states. So the density of states, okay. So the k bar, the allowed value of the momenta are like we've seen before many times. These are the allowed wave vectors. These are the allowed plane waves with periodic boundary conditions, where nx, ny, and nz are integers. So the density of states, so this will be equal to, or rather the number of states between, let's say, uh, E and t plus E dE is going to be equal to B by 2 pi whole cube times 4 pi k squared dk. This is the volume in the k space uh, of the region we're interested in. So we have E is equal to h bar ck. So k is E by h bar c, and dk is dE by h bar c. So that means this thing is equal to um, V by 8 V by 2 pi square times E square dE by h bar c whole cube. So this is for a single value of the polarization, but we have two possible polarization states for a photon. So the density of states would have to be multiplied by 2. So this is for the two polarizations. And so finally, the density of states is V by pi square h bar c and cube E square d E square. So so if you notice, so this is in 3 dimensions with linear dispersion, right? So we have already discussed the general uh, form of the density of states for a general spatial dimension and the dispersion. So so we know that the density of states goes as e to the d by n minus 1, like we have discussed many times. Yeah, so it is indeed that instead of states goes as e square. Yeah, but we did this calculation again just to get all the factors exactly right. So, so now that we have the density of states, we can write uh, the partition function, or rather, the logarithm of the partition function. Uh, so we can write this as an integral over the possible values of energies. Yeah, hope I got that right. Yeah, it's all right. So now the free energy is minus kBT log set. So that's kBT times. Yeah, let's also put in the density of states here. So that's P times kBT by pi square h bar c whole cube integral d e square 1 minus a to the minus beta. Okay, so this is the free energy. Uh, so now we can, I mean, once we have the free energy, we can calculate any thermodynamic quantity we want. So, so before uh, we go to do the next steps, I mean, let's just write this as an integral over a dimensionless quantity. So, yeah, again, quite naturally, we can just use the temperature scale beta to do this. So then the free energy will be, so we will get a factor of kBT whole cube because of this substitution, change of variable. So, so finally we have this kBT to the power 4. And this is integral. This is, yeah, so this is just some real number. It doesn't involve any physical parameters of the system. It's just some real number. So yeah, we can also write this in terms of some Riemann zeta function. Uh, uh, so so I think yeah, let's do some integration by parts. Uh, so if you do an integration by parts by taking this, uh, yeah, by taking this second factor as one which we differentiate, this will become e to the minus x. So yeah, so this term will be 0. This goes to 0 for both these upper and lower limits. So the free energy will be minus b kbt 4 by pi square h bar c cube. So we get a 3 from here. And finally, this is integral. So this is nothing but uh, G4 G4 of 1 times gamma 4. So gamma 4 is 3 factorial 6. So it is 6 times Riemann zeta uh, of 4. Yeah, so finally this is minus 2b by pi square. Let's put the constant here. So this is the free energy. Yeah, so once we have the free energy, we can calculate any quantity we want. So we can calculate the expectation value of energy, entropy, and so on. Yeah, but we can just also uh, use the fact that we know uh, the average number of particles in a given uh, state. So the number of particles or the number of photons, the mean value of the number of photons is going to be yeah, so this factor of 1 by e to the beta e minus 1, uh, that is the Bose distribution function, or simply the Bose function. So that tells us the average occupancy of a given state. Yeah, so now we can just write this as using this expression for the density of states. Finally, making this change of variable, we have this is yeah. So we would get we will get the for the Bose integral g3 of x. Sorry, g3 of 1. Uh, bringing all the constants together, so that would be uh, Riemann zeta of 3 times gamma of 3, which is 2. This is the uh, mean number of photons at temperature T. Yeah, so we still need the expectation value of energy and the entropy. So the expectation value of energy is again simply, yeah, again just substituting for the density of states and making this change of variable. Uh, can write this as times of course there is uh, one extra factor of e in the numerator in this integrand. So we'll be able to write this as Riemann zeta of 4 times gamma 4. So it is 6 Riemann zeta 4 by pi square h bar c whole cube. Yeah, kBt. Sorry, yeah, this is this is kBt to the power 4. So when we make the change of variable, so we have something like dE times e cube. Yeah, so we will get kBt to the power 4. So that means the uh, the mean energy. So yeah, there is also the volume. Yeah, so the energy density in a box of photons uh, goes as the temperature raised to the power 4. So this is the Stefan Boltzmann law. So yeah, so now let's calculate one more quantity and we'll be good to uh, uh, we'll be good to find what is asked in the question. So we also have to calculate the entropy. Yeah, so we have calculated free energy, so we can just calculate entropy from that also. Yeah, so the entropy, or sorry, the free energy, uh, if you look at the differential of free energy, so this is the SPdV minus SdT. So the entropy is nothing but minus dou F by dou T at constant volume. Yeah, so we have the free energy in this expression. So we can so we need to take the uh, derivative with respect to temperature. So that is equal. So that will give us uh, so this is going to be 8 Riemann zeta 4. I think pi square kb to the 4 t cube, and Yeah, pi h bar c all cube times v. So this is the entropy. And yeah, so for all these quantities, if uh, in case I got some of these factors wrong when going from this to zeta function, yeah, if I have missed some factors, uh, yeah, then I'm sorry about that. So please check with some reference. But yeah, but I think they're correct. Uh, so what we'll be interested in is the functional dependence uh, of these quantities on the temperature. Yeah, of course, but these factors are also important. But yeah, uh, so please check these factors again. Uh, yeah, so this is the entropy. What we want is the entropy per particle or entropy per photon. So S by expectation value of n. Yeah, so we have calculated that here. Yeah, so both of these go as t cube. So we are going to get a constant here in this case. Uh, so that's 2 row of 3. Sorry, yeah, so this is 8, 4 times kb divided by 2 zeta of 3. Yeah, so it is 4 zeta of 4 by zeta of 3 times kb. Okay, so zeta of 4 is pi to the 4 by 90, like we discussed. So it's going to be, yeah, something like this, I guess. Yeah, but please check these factors. Let me just leave it like this. Yeah, so this is the entropy per particle. And finally, the energy per particle, or energy per photon. Uh, so we're going to have the energy per photon uh, proportional to the temperature. Yeah, we can see this goes as T cube. The number of photons goes as T cube, but the energy goes as 2 to the 4. So yeah, yeah, here. So now that means this is going to be equal to 6 row of 4 by 2 row of 3, I think, times kBt. Yeah, so this is the energy per photon. All right, so let's move to the next problem. Yeah, so this question is about the photon gas in d spatial dimensions. So what we discussed just now is in 3 spatial dimensions. So what we're interested in is how the total energy inside a photon, uh, like the total energy of a photon gas or a box of photons kept at temperature T depends on the temperature. Yeah. So uh, this is like a simple exercise in uh, doing kind of like dimensional analysis, you can say, because uh, yeah. So we'll be using how the density of states depends on the energy, and then we're going to pull out the temperature dependence we need from the integrals. So, uh, so the energy of the single particle states, E of k, this is still h bar c k, right? So it is still linear dispersion. By photon gas, we mean some massless relativistic bosons. Uh, so the density of states G of E is going to be some constant A times e to the d minus 1. Okay, because these excitations are linearly dispersing in the momenta. So this is how the density of state looks, and what we need is the average value of the total energy, which is so we can write this as yeah. Now again the same old trick. So we can extract the temperature dependence by making this change of variable, so that this becomes, and this integral is nothing but Riemann zeta of t plus 1 times gamma of t plus 1. So the expectation value of energy, uh, the total energy in the cavity is, yeah. So yeah, yeah. Importantly, this A is a quantity which depends on the volume. In particular, it is proportional to the volume of the system, the d-dimensional volume of the system. So A is some little a times capital V, the volume. So the energy volume is going to be, and the heat capacity, CV, is then proportional to T to the D. So in three dimensions, we know it goes as T cube. In D dimensions, it's T to the D. All right. Yeah. So let's move on to the next problem. Yeah, so in this example, yeah, so this is in fact very similar to what we did in the previous problem. Uh, so so this is in some d-dimensional system again with a different dispersion. Just to comment about why we care about these problems. I mean, so why do we care about some d-dimensional system? So it turns out that in condensed matter systems, you can have systems which or in which the excitations or the particles move effectively in only, let's say, two dimensions or let's say one dimension. So you can have some interactions and so due to whatever reasons, so particles effectively behave as if they're confined to move only in one direction. The interesting or rather the important contributions to various quantities like heat capacity, all these things can be understood by treating these systems as effective low dimensional systems. So yeah, so that's why we do these problems of d-dimensional fermionic gas, d-dimensional bosonic gas, and so on. And you can also get, like in condensed matter systems, you can get like a variety of dispersions. You can have excitations with various dispersions in various contexts. So, so for example, phonons, you see that phonons, which are nothing but the excitations associated with lattice vibrations, the collective excitations of lattice. So these approximately have linear dispersion for small k. Uh, or you can have in a magnetic system like let's say a ferromagnetic system. In ferromagnet, you can have certain excitations uh, which are called magnons. So there, uh, these excitations disperse quadratically. Yeah. So all these different cases are actually physically interesting to describe various phenomena. Yeah. So it's just not simply some mathematical exercise. Yeah. So there is some usefulness to doing this. I mean, to thinking about some general dispersion in let's say d-dimensional system. Yeah. So d is equal to 1, 2, and 3 are of most interest. So yeah. So let's get started with the problem with that motivation aside. Yeah. So and one important property of these excitations is that, at least in this case, so in this problem, the excitations that we are going to be concerned about, those are bosonic excitations, and importantly, the number of these excitations is not conserved. Okay, uh, so they don't condense. So it is very similar to the photon gas in the sense that even in the canonical ensemble, we have to allow uh, various microstates with different total number of particles. I mean, so we have to allow all the microstates with varying total number of particles. So there's no chemical potential, or let's say you can set it to zero. Uh, yeah. So now with this, uh, uh, yeah. So with this detailed, I mean, with this detail being mentioned, so let's try to solve for the total energy. Yeah. So first of all, we start with the density of states. So the density of states is again, like we said before, it is e to the d by n minus 1. It is proportional, sorry, it is proportional to the e to the d by n minus 1. So this is the so this is to show that the density of states is proportional to the volume of the system times some constant, and the total energy then is going to be okay, and the energy is equal to this. Yeah, so this is nothing but zeta of d by n plus 1 times gamma of d by n plus 1. So finally, this is equal to this. And the heat capacity, which is what we want, is proportional to, or specific heat capacity is proportional to T to the d by n. So that means, so if we go back to these examples here, uh, so for phonons, they disperse linearly. Uh, I mean, it's a reasonable approximation for small momenta. So the low temperature specific heat for phonons. So in 3 dimensions, if you look at solids or if you look at crystals, the phonon contribution to specific heat equals as T cube. And if you have some, let's say, some magnetic material, then the magnon contribution. So there are these gapless excitations called magnons, which disperse as k square. So this magnon contribution, we write ferromagnetic. So the maximum contribution to the specific heat is proportional to T to the 3 by 2. So these are things you can verify experimentally, or rather, uh, in some cases, uh, that you can measure the specific heat of an unknown material and infer from that what kind of excitations the system has. So yeah, so this is just to show as an example how the specific heat has contributions from various degrees of freedom, and how the temperature dependence of the specific heat uh, changes if you change the dispersion, and how, for example, one can infer what kind of excitations are there in the system by probing the specific heat. All right, so that is that's about this problem. All right, so let's move to the next problem. Yeah, so now we have so far we have discussed the thermodynamics of bosons, which are not conserved. Yeah, so now here we are going to consider bosons, non-interacting bosons, which are conserved. So the total number of bosons, if you or rather uh, the total number of these kind of particles, if you keep in a box, it's going to be conserved. Yeah, so uh, uh, yeah, so we are going to consider this problem in the grand canonical ensemble, and I mean, like in the lectures, you would have seen that for a three-dimensional Bose gas, there is a phase transition at a finite temperature. Uh, so if you consider non-interacting bosons in 3 dimensions, at finite temperature, some temperature Tc, which is non-zero, you have a phase transition into what is called a Bose-Einstein condensate. Yeah, so now this problem is about the existence of a phase transition uh, at a finite temperature in the case of a two-dimensional gas of non-interacting bosons. Okay, uh, so to be clear, the dispersion is still, let's say, the standard quadratic. It's a non-relativistic quadratic dispersion. So if you remember last time, we showed that for the quadratic dispersion in 2 dimensions, the density of states is a constant. Yeah, yeah. So we can quickly see that from this formula. We know that it goes as e to the d by m minus 1. Yeah, so in this case, d is equal to 2 and m is also equal to 2. So the density of states is a constant. Yeah, so to find out whether there's a phase transition at any finite temperature or not, we can just look at the particle number equation and see and try to see whether it is possible to choose a fugacity or chemical potential such that there is no macroscopic number of particles in the single particle ground state. So yeah, let's start with the particle number equation. So the particle number equation tells us that the number of particles, or rather the average number of particles, should be equal to what we want. Uh, oh, sorry, yeah. So we are doing particle conserved boson. So we have Z fugacity here, and it is in fact we have to find the fugacity such that this equation is satisfied for a given temperature. Yeah. So in this case of two-dimensional system with quadratically dispersing excitations, the density of states is a constant. So this is going to be all right. So yeah, let's just do the usual change of variable so that we can write this uh, as some function of temperature times our amine. So this will be a kBT times our familiar friend. Yeah. So we have this Bose-Einstein function. This is nothing but G1 of Z. So in fact, this integral can be done exactly. So even the so if you remember last week, the Fermi-Dirac integral, when the density of states is a constant, uh, uh, I mean the integral for the number of particles uh, when the density of states is a constant, that could also be done exactly. Yeah, so G1 of Z is like we discussed at the start of this session, minus log 1 minus Z. Yeah, so now our job uh, is to find whether there is a phase transition. Okay, so now let's say uh, let's just write this as expectation of n is equal to so this is yeah, so G1 of Z is Z to the m by m to the n, so which is just equal to uh, yeah, sorry, by m to the n. So it is going to be equal to by n, so which is nothing but Z plus Z squared by 2. Yeah, of course, and so on. Yeah, so now let's ask the following question. So keep n fixed, keep expectation value of number fixed, and decrease t. I mean, take it to zero. Take t to zero. Then is there a solution for this equation? By this, I mean this equation, the particle number equation. So if there is no solution, then oh sorry, let me be more clear. So is there a solution for this equation with some z less than 1? So the chemical potential has to be negative. So the fugacity has to be less than 1. So if there is no solution for this equation, which is what we'll find in the case of 3 dimensions, in the case of a 3-dimensional Bose gas, so that means we have done some mistake by omitting the occupancy of the low-lying states near zero, the low-lying single particle states near zero energy. So we'll have to add those contributions by hand, and then we'll see that uh, there'll be there'll be a solution. So it all boils down to uh, checking whether this function on the right hand side. So remember, okay, let's start with this. So the number of particles is fixed, but we are decreasing the temperature uh, to very low to very low values, uh, like however low it may be. Uh, and this should be equal to whatever is there on the right hand side. So now the important point is that as you decrease the temperature, keeping the number of particles fixed, this quantity on the left hand side is going to blow up, right? So this quantity blows up as t goes to zero, or it becomes very large as t goes to zero. So now the question is, can the RHS keep pace with this? So can you find some Z so that however large the left hand side may be, there is some solution for this equation. Yeah, so in the case of the three-dimensional gas, uh, what happens is that as you take Z to the maximum value allowed, Z equal to 1, you see that the right hand side is bounded from above. So it cannot exceed some given value. But the left hand side, on the other hand, it is going to blow up as you take temperature to zero. Yeah, so we are missing out on some macroscopic number of states, and we have to correct this uh, uh, by explicitly adding the contributions due to the uh, low-lying single particle states. But here in this case, so this RHS, this thing, minus log 1 minus z, this is not bounded. This is not bounded for z less than 1. So as you take, so let us be more clear. It's not bounded from the above. So as z tends to 1, the RHS also tends to infinity. So uh, indeed, this can keep pace with the left-hand side, and there is a solution to this equation for any temperature. There is a z less than 1, which can solve this for you. So that means that even if you want to add, let's say by hand, let's say the contribution the due to the let's say the zero energy state, yeah, you can add that and solve it, but you won't get a macroscopic occupancy in the ground state for any temperature greater than zero. So so also this can also be seen because if you just put z equal to 1 here, you get 1 plus 1 by 2 plus 1 by 3 and so on. Yeah, so this sum does not converge to a finite value. Uh, so that means you can always find z less than 1. So you can always find, with no macroscopic occupancy of the single particle ground state. Sorry. Yeah. Yeah, so there is no phase transition for any t less than Tc. Oh, sorry. Uh, there is no phase transition for any t greater than 0. All right. Okay, yeah. So let's move to the next problem. Yeah. So now this is again back to 3 dimensions. So that was just an exercise to show that there's no Bose-Einstein condensation at finite temperature in 2 dimensions. So also, yeah, just one more comment. So here, in the case of a three-dimensional uh, gas, the density of states uh, goes as square root e near equal to 0. So replacing the sum with the integral there, is very problematic for low temperatures because we're going to miss out on uh, the contributions of uh, like any state near equal to zero. Uh, but here, for the case of two-dimensional gas, the density of states is constant. It's finite. I mean, as e goes to zero, it doesn't go to zero. Yeah, it's so it yeah, it turns out is yeah, it's not so bad. Not so bad replacing the sum with the integral, and yeah, replacing sum with the integral, and yeah, so just wanted to make that comment. Okay, all right. So yeah, so now this is again about the three-dimensional gas and calculating various thermodynamic quantities for it, and in particular near. In the lectures you would have seen that uh, yeah, so in the lectures you would have seen that uh, there is a critical temperature Tc, which is positive. The specific and the specific heat at this temperature is uh, shows the singularity. So the specific heat is continuous, but it has a kink or it has a cusp. Something like this. So the specific heat looks like this. Uh, so here it goes as T to the 3 by 2, and it attains the the equipartition uh, classical value of 3 by 2 kPt. So this is yeah. So sorry, the specific heat is 3 by 2 kP. The equipartition specific heat, the classical result is 3 by 2 kP. Yeah. So it approaches this. So the important point here is that there's a cusp in the specific heat at the critical point. So this is the specific heat at constant volume. What about the specific heat Cp or the heat capacity Cp? What kind of singularity does it show at the critical point? That is the that is mainly what we're interested in. So notice that the Cv is continuous at T equal to Tc, but of course this is discontinuous. The derivative of Cv with respect to temperature, this is discontinuous. This is a singularity. What about the singularity in Cp? Yeah, this is what we will be trying to find in this problem. Okay. Yeah. So the some steps have been given. So let's just follow that. Uh, yeah. So before this, we'll need one more. Uh, yeah, we'll need one more result, which is about this dou z by dou t at constant volume. This thing we have in the denominator. Yeah, so let's start with how much time do we have? Yeah, we have enough time. So yeah, let's start with uh, this quantity dou z by uh, dou t at constant volume. Okay, so our job is to express this in terms of the Bose-Einstein function. So let us first start with this calculation. Yeah, so we did a similar calculation last time for fermions. Uh, yeah, these are very similar. It's just that I mean the calculation part, uh, doing the calculation, doing the integrals, and uh, yeah, this sort of stuff is like very similar. But of course, these functions have strikingly different properties, and of course, and as a result, the physics is strikingly different for fermions and bosons. But I'm just saying, uh, doing the algebra part is somewhat similar. Uh, okay, so we again start with the particle number equation. So it says that n is yeah, we've written this so many times. Okay, so g of e is proportional to root e. So keep let's just leave it as some constant, like a v times square root e. Yeah, we don't need these constants here in this problem. So yeah, let's not uh, let's not take the pain of 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 keeping track of these constants. So this is going to be and doing the usual stuff. Yeah, so this is nothing but some constant times uh, t to the 3 by 2 volume, of course, and this is g 3 by 2 of z. So we want to we want to find the derivative of z with respect to temperature at constant volume. So let's just take a derivative of this equation at constant volume. So the number of particles is fixed. So that means dou by dou t of this thing at constant volume is 0. So yeah, so now we have a derivative of the Bose-Einstein function. Yeah, we discussed this uh, at the start of the session. This is going to be equal to, so first of all, we can just write this as dou by dou z of times dou z by dou t at constant volume. Yeah, so this is nothing but g half of z by z. So what we see is that 3 by 2 g3 by 2 of z plus t. Yeah, so from this we can find 1 by z dou z by dou t at constant volume is going to be minus 3 by 2t g3 by 2 of z by g1 by 2 of z. So this is the first result we need. And it wants me to turn off the microphone. Okay, so yeah, so now let's continue with the second step or the calculation of this quantity, dou z by dou t at constant pressure. So as we'll see, these quantities, I mean these derivatives that we are calculating, these will be useful for the calculation of heat capacities. So the heat capacities can be expressed in terms of these quantities. So yeah, so let's calculate this now. So we can just start with the pressure equation now. I mean, some expression for pressure in terms of the Bose-Einstein functions, and then we can we can take a derivative keeping the keeping the pressure constant. That would give us this quantity. Just a minute. Yeah. Okay. So yeah. So pressure we can get from free energy, which is minus dou F by dou V at constant temperature. And free energy, okay, yeah, yeah, I don't remember this on the top of my head. So yeah, so let's do this. So F is minus kBT log Z. Yeah, in fact, wait. Yeah, so I mean, we need not do all this. It is equivalent, but let's save some time by just using this, uh, using the fact that the pressure is related to the energy density. So pressure is 2 by 3 times energy density. So this is true. Yeah. So if you remember, we derived this for the Fermi gas. So this is true at all temperatures. Yeah. So this will also be true for the Bose gas at all temperatures. So the pressure, yeah. So the pressure is then equal to, so the energy density. Yeah. This we can quickly write as this integral. Some constants are there. Yeah. So we're going to get a factor of T to the 5, I mean, we're going to get a dependence uh, uh, like so. So we're going to get a T raised to the 5 by 2 here. Yeah, and we're going to get, so this is going to become x to the uh, 3 by 2. Yeah, that's all right. So yeah, so this is g 5 by 2 of z times some constant. So we have absorbed all the constants in here. Yeah, so yeah, this looks very similar to the particle number equation. So here we have the particle number is, or the density is proportional to t to the 3 by 2 times g of 3 by 2, or g 3 by 2 of z. Here it is t to the 5 by 2 times g 5 by 2 of z. Yeah, so now we can just take pressure is, we can take derivative keeping pressure constant. And doing a similar calculation, we can see that 1 by z by dou t at constant pressure is going to be minus 5 by 3 or 5 by 2. Yeah, let's let's come to that in a moment. But this is going to be g 5 by 2 of z. Yeah, so this calculation, let me just check. Yeah, it's going to be yeah, 5 by 2t. Yes. Yeah, so this calculation is going to proceed very similar to what we did here. Just using the recurrence relation for uh, the derivative of the Bose-Einstein function, we can calculate this. Yeah, so this much is done, and now uh, yeah, let's move to the main part of the problem, which is to find the uh, yeah, it's to find the specific the heat capacities and the ratio of heat capacities. Okay, so now the third part of the problem. So express is expressing CVCP in terms of these derivatives that we have spent so time calculating. Yeah, so just from the definition, we can see that CV is the uh, yeah, so it's T dou S by uh, dou S by dou T at constant volume. Yeah, and CP is T dou S by dou P at constant pressure. Sorry. And now let us use this fact that S is a function of only Z. Yeah, so yeah, of course, S will also depend on one extensive quantity. So let's say S is a function of n, t, and mu. Yeah, so it is easy to show this. So we also showed this for the Fermi gas the week before this. So the idea is to just use the Euler's relation, and then we can express entropy in terms of all these various thermodynamic quantities like energy, pressure, and so on. And then at the end of the day, you'll see that uh, the entropy per particle can be expressed only as a function of the fugacity. So entropy will be extensive in the number of particles, or I mean, entropy is extensive. So the entropy per particle is a function of only T and mu. So this is a function of some function of uh, let's say little less something. Yeah. Uh, so we have shown this for the Fermi gas. This is also very similar. This derivation is also very similar. So now we can use this to write that CV is T times dou S by dou Z times dou Z by dou T at constant volume. Yeah, so the function S depends on temperature through fugacity, through only through fugacity. So we can write this, and similarly Cp is dou S by dou Z times dou Z by dou T at constant pressure. Okay, so Cp by Cv or gamma, the ratio of specific heats, is dou Z by dou T at constant pressure divided by dou Z by dou T at constant volume. Yeah, so this is what has been asked in this question, asked to be shown in this question. Yeah. So now let us make use of what we derived about these derivatives. So this is going to be phi by 2 g phi by 2 by g3 by 2 divided by, okay, so this is going to be phi by 3 times g phi by 2 of z times g1 by 2 of z by g3 by 2 of z whole square. So this is Cp by Cv. Yeah, so immediately we can see something. So okay, now the point of interest is the behavior of Cp at or near t equal to Tc. So Z is uh, close to 1. Okay, so what happens to this to the heat capacity at constant pressure, Cp? Okay, so first note that in this limit, so Cv exists in this limit. Cv is a continuous function, even at the critical point. So Cv is finite and continuous at t equal to Tc. Uh, so let us look at what happens to the right hand side. So G 5 by 2 of 1, or let's say G, so G, we know that Gn of 1 is simply Riemann zeta of n. Yeah, yeah, that's right. So that means that G 5 by 2 of 1. So as you take z to 1 in this function, uh, this is uh, this is a finite number. Yeah, so I mean it is some real number, it's some positive real number. So uh, this uh, this infinite sum will converge, and similarly G 3 by 2 of 1 is Riemann zeta of 3 by 2. This also is finite, so it converges. But yeah, we also have G 1 by 2 of Z in this expression in the numerator. So let's see what that is. So G 1 by 2 of Z would be Z plus Z squared by 2 to the 1 by 2. Yeah, plus Z cubed by 3 to the 1 by 2, and so on. So if you just put Z equal to 1 here, so that would be a sum like 1 plus 1 by root 2 plus 1 by root 3 plus so on. So this sum does not converge. So G 1 by 2 of 1 is not finite. So it blows up. So okay, or another way of saying is G 1 by 2 of Z goes to infinity as you take Z to infinity, as you take Z to 1. So near the critical point, this quantity blows up. So let's just write this equation again. Cp by Cv is G5 by 2 of Z. Yeah, so this is the equation we had. Some 5 by 3 is there. Yeah. So now we just discussed that as you take Z to 1, this quantity, G 1 by 2 of Z blows up, but the remaining quantities are finite, so the RHS blows up. The RHS goes to infinity. So what can you say about Cp? So we know that Cv is finite, so that means so that only leaves us with one choice. So Cp has to blow up, or Cp has to go to infinity near t equal to Tc. So as you approach the critical point, the heat capacity Cp diverges. Let me just write diverges. Okay. Yeah. So we have now established that CP diverges near the critical point, and what is left to be done is finding the nature of divergence. So how does it diverge? What is the nature of divergence? So uh, how does CP look near T equal to TC? Yeah. Hmm, so in the question it is so it's also given that it will diverge as 1 over T minus TC. So we have to show that this is the nature of divergence of CP. Okay, yeah, let's try to do that in the remaining time. So since both these quantities are finite, we just have to understand the nature of divergence of this function g1 by 2 of z as z goes to 1. Yeah, sure. When z is when you take z to 1, it diverges, but how exactly does it diverge? Yeah, this is what we want to understand. Yeah, so let's look at this integral definition of this thing. Yeah, so this is the definition of this function. Yeah, so let's say, so we are going to take z to 1, or equivalently, we can just define z as something e to the minus y and take y to 0. Yeah, uh, so then we can write this, let's see, so we can write this as, so this is going to be e to the x plus y minus 1. So the divergence will actually come due to the integral near x equal to 0. So notice that when y is exactly 0, when you put y equal to 0, uh, the integrand looks like x to the minus 3 by 2. So that is where the divergence is coming from. So uh, sure, even when y is not equal to 0, the integrand will diverge, but the integrand will diverge, but that is just a 1 by square root x divergence for the integrand near x equal to 0. So the integral is finite. converges. But when y is exactly equal to 0, the integrand diverges as x to the minus 3 by 2, and that is the source of uh, divergence of the integral. Yeah, I hope it made sense. Yeah, so we can just write this as, since we are interested, I mean, so to capture the divergence, we can uh, we can uh, we can use the fact that the divergence is coming near x equal to 0, near the integral from the integral near x equal to 0. So we can just assume that this is x is small, and can do this. Yeah. So what you can show is that if you can do this integral, and this goes as 1 by square root y, I think. Yeah. Yes. Yeah. So yeah, you can do this integral and show that this goes as 1 by square root y. And so g 1 by 2 of z, going back to the uh, original, I mean this function. So this goes as some constant times. Yeah, we're interested only in the divergence. So remember y is minus log z. So it's 1 by square root minus log z. So z is less than 1. So we are approaching z1 from below. So yeah, so this is fine. Whatever is inside the square root is positive. Yeah, so this is how the Bose-Einstein function g 1 by 2 diverges near z, z going to 1. As z tends to 1 minus. Okay, so yeah, you can clearly see this diverges. Yeah, so this is what we want, but we are still not done yet. So we know how this function diverges as a function of z, but we need ultimately we need the divergence I mean, we need to express the quantity as a function of t minus tc. So then we need to find uh, how is t minus tc related to z. Yeah, so and now we have to find this. Yeah, so this can be done simply from the expression for the number of particles. I mean, we can just take this expression. So let's say t is greater than tc. So we can write the particle equation. It's going to be and exactly at t equal to tc, this is also equal to tc to the 3 by 2 times g 3 by 2 of 1. Yeah, so we can just divide these two equations to get t by tc to the power 3 by 2 is or times so this is equal to g 3 by 2 of 1. Uh, yeah, so so now we can expand this near z equal to 1, and then so if you expand g3 by 2, so first of all, let's just write this as let's just write t by tc is equal to t3 by 2 of z whole to the 2 by 3. So we want to expand this near z equal to 1, because I mean we want to find the relation between t minus tc and z. This is going to be 3 g3 by 2 of 1 plus dou by dou z of g3 by 2 of z at z equal to 1 times z minus 1 plus so on so on. Yeah, we just did a Taylor expansion. So yeah, we know this is now related to g1 by 2. So let's just substitute z equal to 1 there. Yeah, so limit, you know, g1 by 2 of z as z tends to 1 times z minus 1. Yeah, so now we can use what we have here, that g1 by 2 goes as 1 by square root minus log z. Yeah, so finally this is what we have. Yeah, so near z equal to 1, this is a small quantity. So so this whole quantity will turn out that it's as small as you take z to 1. So you can expand this and find t in terms of z. So you can get t minus tc in terms of z. And then finally, we can go back to what we want, and what we want is how just g1 by 2 of z goes. So so finally, you'll see that. So what you will find is that. So what you'll find is that I think square root minus log z is proportional to t minus tc. Uh, z goes to so this is near z1. So as z goes to 1, this is how the fugacity depends on the uh, the difference of temperature from the critical point. So that means that finally our heat capacity, so it has this g1 by 2 of z dependence or divergence. So that is 1 by square root minus log z. So this goes as 1 by t minus tc. Yeah, so for T greater than Tc, this is how the C capacity Cp looks. So this is how it diverges. So naturally, gamma also diverges like this because Cv is a constant. Cv is a finite quantity at the critical point. Yeah, so finally, yeah, so this is yeah, some lengthy calculation. So you have to know how to how to get the correct correct asymptotic behavior of these Bose-Einstein functions in the limit z going to 1. So we have to know the divergences of these functions. Yeah. So yeah. So most of the time has been spent trying to understand these divergences, trying to see uh, how the divergence of G1 by 2 function is near z equal to 1. Yeah, but ultimately the result is that for non-interacting Bose gas in 3 dimensions with quadratic dispersion, the heat capacity constant volume is finite, it is continuous, but the heat capacity constant pressure Cp diverges, and it diverges as 1 by T minus Tc. Yeah, so these kind of divergences in thermodynamic quantities, or in general any singularity in the thermodynamic quantities, is yeah. So they are very important uh, things which characterize the phase transition. The nature of singularities of various thermodynamic quantities, how these quantities diverge. Yeah, that is very important, and it has a certain universal uh, aspect. Yeah, so just wanted to emphasize that uh, yeah, so it's important to think about or rather so it's, so it's important to note how various thermodynamic quantities diverge near a phase transition. So yeah, so this one example we saw how the uh, the quantity Cp diverges. Okay, all right. So that's all I have for today, and yeah, it still wants me to turn off the microphone. Okay, yeah, all right. Thank you. See you.